Hi, this is Crossdot and Nabla, and in today's video, we're going to be covering over section 13.2, covering double integrals over non-rectangular regions, right? So in our previous video, we covered over what this would look like in rectangular regions, and like in single variable calculus, it's really straightforward. You just plug and chug, your antiderivatives, and you move on. However, now, for double integrals over non-rectangular regions, we have to consider our bounds. We have to consider what shapes the functions make, right? And you have to be cognizant of all that as you're going along, right? And instead of it being over a rectangle, we have it over a simple closed curve. And that's something you're going to hear quite a bit in Calculus 3, a simple closed curve. And what that just means is, like, for example, this region S right here is a simple closed curve. What that means is that you can walk from one spot on this curve to another spot without intersecting within the curve, right? So a figure eight, for example, technically isn't a simple curve because you have to walk across one end to get to the other, right? Like this, you're going to cross over some arbitrary area, right? Mark that in red. In this case, a simple closed curve, we're usually going to be dealing with this for these types of problems. And if you're not, you're probably going to have to use a graphing calculator or something like Desmos, which we'll be using in this video to actually show the bounds. But you would have to use Desmos to graph or model these integrals if they weren't simple closed curves. And if a curve is closed, it's kind of straightforward. That just means that every point along the boundary is continuous. You can walk on in a straight line and you wouldn't fall into the abyss, right? That's essentially what that means. And right here, we have the volume equals the double integral over the region S, f of xy dA, relatively straightforward, same thing from 13.1. And then we have our dy dx, again, which is just our dA, which you remember, from phi sub 1x to phi sub 2x. So it's going from top to bottom. And then for this one, we have c to d, h sub 1, y to h sub 2y. So this is going right to left. So this one is going right to left. This one's going top to bottom, right? And overall, it shouldn't be too bad once we go over the first couple of examples. Let's jump right into it. All right, example 1. So we're trying to find the double integral over the region S, 5 dA, where S is the triangle with vertices 0, 0, 0, 4, and 1, 4. Now, there are two ways we can do this, and I'm going to do the very, very cheap way to actually solve for the volume of this first off, right? So what we can do is we can see that this is 1, and this is 1, 1, 1, 1, or it's 4, right? So then we have our triangle right here. So it's going to be 1 times 4 divided by 2 equals 2, base times height over 2, right? However, what we can do is, if we know our function is 5, right, we can pull this out as a constant. That's one of the rules that we use from single variable integration. Now we can use a multivariable integration. This is a constant, regardless if it's x or y, right? So what we can do now is just raise everything up to z equals 5. And it's kind of like a rudimentary drawing, but what we can say now is that this is going to be z equals 5, like this. And essentially, we have a triangular prism. We have 2 times 5 equals 10 units cubed. Now, that's kind of the cheap way to do it. However, I will show the more rigorous way to actually apply this double integral. And if you want to try this on your own, feel free to pause the video, but let's get right into it. Okay, so I'm going to start off right here, and we have our points, right? So we have y equals 4x here, because this goes from 0, 0 to 1, 4. And we're just writing all the points for the sake of saliency on our end. So we have all the points, right? And I'm thinking, how can we make our lives a little bit easier? So we can, what can we integrate to get this triangle to exist, right? So I see right here we have y equals 4, x equals 0, and then we have some imaginary x equals 1 right here, right? So let's actually get our double integral done. I think I'm going to write it in dy dx, because I like that y equals 4x. there. It's pretty straightforward. So we're going to bring out the 5. It's a constant. dy dx. And then for dy dx, if we're integrating with respect to y, actually no, sorry, it would be dx dy because we want it to be in terms of y first. Y equals 4x. Actually, sorry. I'm even flipping my own words now. Whew, okay. It would be 4x right here because y equals 4x like that. And then you would have 4 on top. And then the x's vary from 0 to 1. And let me actually rewrite it like that, 1 like that. And the reason why we wrote it like that is kind of important because if we look at this, we can actually analyze it now like this. If we wrote this out, right? So 4 is our top bound, right? And then 4x is our bottom bound, which means that this is always going to be going up like this, right? So that's going to be something that we're cognizant of. And the bounds from 0 to 1 is because this goes from here to here, right? And that's also important for us to understand as well, right? Now we can just integrate this kind of straightforward. And it really is just straightforward. We're just plugging and chugging in numbers at this point. And yeah, let's just get right into it. So for this, we have y evaluated from 4x to 4. Let's actually write this in red because I like to do the integration in red instead, so it's easier for you, the viewer, to see. So we get y is from 4x to 4. This becomes 4 minus 4x. That's just one of the most straightforward things you'll see in any calculus video. We don't have to go through the whole process, right? And we got 0 to 1, 4 minus 4x dx. And then we can integrate this. We get 4x minus 2x squared, evaluated from 0 to 1. So then we also don't forget about the 5 either, right? So it's going to be 4 times 1 minus 2 times 1 squared minus 0, 4 minus 2 is 2. 2 times 5 equals 10. 10 units cubed. And that's our final answer. Same thing as above. And that actually works for really simple shapes like triangles. And eventually, in our next video, we're actually going to cover over circles as well for polar coordinates. And now, for example 2, we're going to evaluate the double integral s over the region S x dA, where S is the region between y equals x and y equals x squared in the first octant. So if you want to try this on your own, feel free to pause the video and let's get right into it. All right, so let's draw out our graph. That's a good enough graph for me, at least. We can always do better, but you know, whatever works. Okay, and we're gonna draw out our graphs in blue. Let's do green actually. I want to be consistent with the image above. So we want it between y equals x and y equals x squared in the first octant, right? So what this means, what this qualifies to us at least, is that we know that x is greater than or equal to 0, y is greater than or equal to 0, z is greater than or equal to 0, and then we can integrate from there, right? And part of the reason why I'm actually just not graphing in 3 variables is because we're only focused on our bounds in 2 variables, and we can just expand that into 3 variables later on if we wanted to, right? In this case, we could have just drawn the graph like this and then gotten our z elsewhere. You don't have to do that, but this is something that I prefer to do because it makes it easier for me to visualize the actual bounds of the graph, right? All right, so let's get back into it. So we have y equals x, and that's good enough, I would say. And then we'll just write y equals x, and then we have y equals x squared, and that one grows a lot quicker, right? So, and I can actually write this one in orange. How about that? Makes our lives a little bit easier. Actually, I have to cut it real quick. So it has to be, if I want it to be orange, we can just do this. We can just do y equals x squared, right? Perfect. So now we see we have to find out where these graphs intersect. So we can just do that real quick. We can do y equals x, x equals y equals x squared minus x equals 0, x minus 1 equals 0, x equals 0 comma 1. So we get 0, 0, and 1 comma 1. Kind of straightforward, very, very easy to identify, but we're still going to go through this because it matters to actually solve this, right? And again, I'm going to use dy dx as my order of integration because I see like a very, very straightforward, like we have this as a parabola, we have it as a linear, a line. It's going to be straightforward for us to solve, right? So then we can do x dy dx. What's on top? It's our line. What's on the bottom? It's our parabola. What's our bounds for our x? So right here, let's dot this in blue. This is 1 comma 1. Dot this right here. That is 0 comma 0. And then we get 0 comma 1. From 0 to 1 as our bounds for our x, right? And now we can actually start integrating. So I'm going to go back to red, and we're going to start integrating this function, right? So in this case, it's going to be x dy. So x is going to be a constant with respect to y. So we're going to get xy evaluated from x squared to x, right? In this case, we're going to get x times x minus x squared times x. So we're going to get x squared minus x cubed. And then we get our new integral, 0 to 1. Well, we don't get a new integral. We get a single integral now, which we have only constants in. So we get x squared minus x cubed dx. And this becomes x cubed over 3 minus x to the 4th over 4, evaluated from 0 to 1. And then we get 1 cubed over minus 3, 1 cubed over 3 minus 1 raised to the 4th over 4. We get 4 over 12, I think. Yeah, 4 over 12 minus 3 over 12. We get 112 as our answer. Pretty cool. And you can actually also do the other order of integration, although it is a little bit more tedious, and we'll actually cover that in our next couple of problems right here, right? In example 3a and example 3b down here, we're going to cover that. Example 3a, b, and c, sorry, yeah. So I have 3 different examples to show that you can rewrite these iterated integrals or double integrals in different orders, right? For 3a, if you want to try this on your own, feel free to pause the video, and let's get right into it. All right, so I'm going to always draw these out, and I'm going to draw them out in the green and orange colors that we talked about above because it's just easier for us to identify, right? So we get this, we're going to get x equals 2y. We could draw, actually, let's first off, before we even do that, let's just get our points of intersection because I feel like that's going to be helpful for us to identify, right? So we get 2y equals y squared minus 2y equals 0, y minus 2 equals 0, y equals 0 comma 2. And then I can also see from our points alone, if we have x equals 2y, x equals y squared, we would get 0, 0, 2 comma 4. Okay, perfect. We're going to use that for later, right? So I'm going to use my first graph as x equals 2y. Okay, and we're going to only do the first quadrant, right? So we'll just do 1, 2, 3, 4. And then we have the x equals y squared, right? So we're going to get this to be like this. Actually, it's a little bit less like that. There you go, that's better. And this would be y equals x squared, y equals 2, no. Sorry, no, not either one of these are right. X equals y squared, and x equals 2y. And our points in red are 0, 0, and 2 comma 4, right? Perfect. And now we know what we can do for our order of integration, right? If we want to go from dx dy to dy dx, so we're flipping the order, we have to do a change of the function in terms of x into the change of the function in terms of y, right? And so for this first one, it'll be pretty straightforward. We're just going to be taking the square root. So then it would become x equals y squared. It would become square root of x equals y, which is a familiar function that we can see right here. And then for our green function, x equals 2y, we have x over 2 equals y. Perfect, right? And now we can use our new function, we can use our new variables, or our change functions, I guess. Not really change, but changing what variable is independent, what variable is dependent, right? Now what we can do is actually set up an order of integration, right? So now we have dy, well, what's on top? We have the orange functions on top. So we can say now that we have some f of xy dy dx. We're changing the order from dx dy to dy dx. And that's going to be square root of x from not square root of x, from x over 2 to square root of x. However, our x values are going to change. It's going to be from, instead of going from 0 to 2 for our y, it's going to be going to, this should actually be 4 comma 2. Now looking back, this should also be 4 comma 2. 4 comma 2. And this is actually going to be 0 comma 4. And these points actually correspond to what we have now, because right here we had 2 for our y and we have 4 for our x, so it'd be 4 comma 2 for our value, our point, right? Same thing here, we have 0 right here, and we also have 0 right here, which also corresponds to this point right here, right? And that is the answer for 3A. For example 3B, if you want to try this on your own, feel free to pause the video, and let's get right into it. All right, so we have our green function. We're just going to label as y equals x. And I'm only going to use the first quadrant because, again, our x and y values are only going to be positive, right, on this interval. Because if we even check, right, x cubed, 1/2 is 1/2 is going to be 1/2 cubed is 1/8, and then 1 cubed is just 1, right? So now we can just do this. And then our x cubed is going to look something like, actually going to look more like that, a little bit more flat at the bottom, right? So we're going to have y equals x cubed. And then we have y equals x. And we can also just shade in. Let's just use a different color. Let's actually use purple. Some type of purple would be nice to use, actually, yeah. Some type of purple to actually indicate our x bounds, right? So our x bounds are actually going to be from here to here. X equals 1/2, x equals 1, and we're integrating along this boundary, right? So now we have to find our points of intersection for these graphs, right? And we'll find them real quick. So this is going to be 1/2, 1/2. This is going to be 1/2, 1/8, because 1/2 cubed is 1/8. And these two share that same point. It's going to be 1 comma 1. Perfect, right? So now, if we're converting from dy dx to dx dy, now we have to be cognizant of a couple of things, right? So along this portion of the graph right here, we're not bounded by the green function. We're actually bounded by the purple dotted line for x equals 1/2, right? So if we're doing dx dy, our left bound is actually going to be as follows. And we're not actually going to integrate this function to f of xy, right? It's just some dummy function that we're using, or placeholder function that we're just using, dx dy, right? So in this case, 1/2 is actually going to be our leftmost value, right? Or in fact, 1/8 is actually going to be our bottommost value, because it's going to be x equals 1/8, y equals 1/8 right here, that we're subbing in for that, right? And then we're going to get 1/2 as our topmost value right here, right? And then 1/2 is also going to be in our in our dx, because of this right here, this is the leftmost portion of it, and then the rightmost portion of it is going to be our cube root of y, right? So let me just fix this real quick. Cube root of y, right? And I probably should have also changed these as well. So it would have been y equals x cubed, cube root, y equals x equals y, right? That's kind of straightforward. And that's our first bound, right? And one thing I should have noted, that first part took me a little bit longer, is that you should be going from the inside out, right? The inside out, because this right here represents your first integration, because it's 1/2 to the cube root of y with respect to x, because y equals the cube root, because x equals the cube root of y, excuse me, right? So that's region 1. And then for region 2, we're going to also use dx dy. I don't like that integral. Let's rewrite it. It's a better one. F of x, y, dx dy. And then our lowermost value is going to be 1/2. Our uppermost value is going to be 1, right? Because that's where they intersect, right here and here. And then for our dx, the rightmost function is going to be the cube root of y. Our leftmost function is going to be just y, right? And if you want to go on Desmos to show this as well, feel free to do so, and we'll actually do that right now. All right, now we're at Desmos, right? And we're seeing these curves right here, right? So the issue with doing this in a singular region is that you have two different leftmost curves, right? This is the most leftmost curve from 1/8 to 1/2, right? So you have to integrate from the black to the red, excuse me, right? On this for your y, but actually no, not for your y, for your x, excuse me. But for your y, you're gonna have to just integrate straightforward from 1/8 to 1/2, right? However, for this, you have a new graph, which is the green right here, and the orange right here. And that's why you have to have those two separate regions, right? From the original function, you only have to do 1 because this function's always going to be above this one, regardless of the bound that it is in, right? However, for this one, you have two leftmost functions, right? And this is actually a good example of looking at your graphs and seeing what order of integration would be more intuitive and more efficient for what problem I'm solving, right? And in this case, writing it as dy dx gave us only one double integral we had to solve. This gave us two double integrals we have to solve, which is more tedious and inefficient, which we don't want in this class, right? A lot of this class is about optimizing and being more efficient with the work that you're doing. And I think this is actually a great shortcut that you can use to look at, okay, now we know if we have two leftmost curves like this on Desmos, I like to color them out just to make it look different, right? We have two leftmost curves now. This would mean two separate regions to integrate, two double integrals. Double integrals already take time as is. Why waste this time if we can just use dy dx instead of dx dy, right? And now for example 3C, we have this. If you want to try this on your own, feel free to pause the video and let's get right into it. All right, so for this, we have our graph, and let's just actually graph this out real quick. So we have x equals y, x equals negative y, and it's bounded from 0 to 1 for our y, right? So we'll just use green like this, and orange for this. Let's use purple for our boundary line. Well, let's actually extend this out further. And this is going to be y equals 1. We're going to have this be x equals negative y. We're going to have this be x equals negative y. Oh, this is not x equals negative y. This is just x equals y. Yeah, there you go. Let's point our dotted blue lines. We're dotted blue right here. It's going to be 1, comma 1, negative 1, comma 1, and then 0, comma 0. Right, so now if we're changing the order from dx dy to dy dx, we have to rewrite this as in terms of y, right? So this is just going to become y equals x, and then y equals negative x, right? And now we can use our standard tricks to solve these double integrals, right? And I think we're going to get two separate regions again, which is fine, but we can still solve for this, right? In this case, we can actually also just draw this as our x equals 0 to cut off the two regions, right? We can also now write out our integrals, right? So for the region 1, we're doing dy dx, right? We're doing dy dx. We're going to be going from top to bottom for our y, right? So our top is 1, our bottom is x, right? Because if I see on this entire interval, yeah, it's always going to be pointing downward towards that, right? And for our x, it's going to go from 0 to 1 for f of x, y, dy dx. And then for region 2, let's see the same thing if that occurs. So for region 1, for this region, we have 1 at the top, negative x on the bottom, and then we have from negative 1 to 0 for our x, right? Because our x is always pointing that way. It's always within this region, right? Oops, let me get back to that. It went all the way down. Jeez Louise. It went all the way up, yeah. We get f of x, y, dy, dx. And when you add up these two regions, you get your final answer, right? Again, this is a good example of seeing how we can actually just rewrite this and you get one singular integral, because in this case right here, one singular double integral, right? In this case, this is always going to be to the left of that on this entire region, right? And it's always going to be bounded from 0 to 1, right? This is taking more time. It's a double integral, two separate double integrals, and that's like too tedious for our being, right? And now to actually evaluate these double integrals, this is something we've been waiting for this entire video. But now that we know the skills to actually to change the order of integration for these double integrals, now we can actually solve for these double integrals in non-rectangular regions, right? And if you want to try this example on your own, feel free to pause the video and let's get right into it. Okay, our trick we have to remember for these x squared plus y squared things are that we're going to have 1 over a arctan of y over a, right? Yeah. And now we can just get rid of the 3 as it's a constant. Move that to the front. And then we get this. Now we get 1 over x squared plus y squared dy dx, right? In this case, we're going to get 3 over x arctan y over x, because we're integrating with respect to y, right? And then we're going to evaluate this from 0 to x. So then we're going to have 3 over x arctan of x over x minus 3 over x arctan of 0. This becomes arctan of 1 minus 3 over x times 0. This goes to 0. So let me get 3 pi over x, 3 pi over 4 x right? And now this is our solution for that first integral. So now we have to go back to rewrite our second integral from 1 to 5 of 3 pi over 4x. And remember, that's because arctan of 1 equals pi over 4, right? And now we can actually solve for the second integral right here. 1 over x dx, which is just going to be ln x evaluated from 1 to 5. And then we're going to get ln of 5 minus 0, because ln of 1 is 0. And we get ln 5 times 3 pi over 4. So we're going to get 3 ln 5 times pi over 4. And you can rewrite this as pi ln 125, because it would be 3. 3 goes into the 5. 5 cubed is 125. Pi ln 125 all over 4 is your final answer. For example 4b, if you want to try this example on your own, feel free to pause the video and let's get right into it. All right, this is our last example of the day. Let's get this done. So I'm going to graph this one out because we don't get the exact region, right? But we do get a couple of things. So let's get our y equals x like this, our purple dot like this. Y equals 2x, y equals x. And then we can now solve for this, right? Something I'm quickly noticing right here is that we have a top minus bottom relationship right here between these two. So we're going to probably use that to solve for this, right? So we're going to rewrite this double integral now like this. dy dx. So it's going to be from x to 2x. And what's our bounds for our x? It's going to be from 0 to 1, right? Because it's always going to be above this right here. And where they actually intersect, which I should have done earlier, is 0, 0, right? And if it was going further down, you would see that this would be, they would intersect at the origin, and then they would just be going down. The 2x would be going down at a more rapid rate than the y equals x graph, right? So then that would be from 0 to 1. And now we can actually solve for this. So we're going to get xy plus y squared over 2, evaluated from x to 2x. So then we're going to get 2x times x plus 2x squared over 2. So we're going to get 2x squared plus 2x squared minus x times x plus x squared over 2. And this is going to become 3x squared over 2. So then we're going to get this to be 4x squared minus 3x squared over 2 equals to 5x squared all over 2. And now we have this for our second integral. Let's bring out the 5/2, that's a constant. And then we can now integrate this. Actually use a red arrow to maintain consistency. I'm a stickler for that. So we get x cubed from 0 to 1. So then we get 5/3. 5/3. Actually, no, it's going to be, let me fix this real quick. It's going to be 5/2 times 1/3 x cubed from 0 to 1. So 5 over 6. 1 cubed minus 0 cubed, so that's irrelevant. This is going to be 5 over 6 as our volume. And that is our final answer, and that is our final problem for this section. Thank you so much for watching, and I hope you guys have a fantastic day.